Okay, hello everyone. So we're getting towards the end of the course, and we're going to have an opportunity to have some lectures from experts in some more advanced areas of transition metal chemistry. And so the first of those will be today from Dr. Megan Jackson. Dr. Jackson did her PhD in electrocatalysis at MIT. And so she's going to give a lecture today in this area, and I hope everyone enjoys it. It will be material that's going to be covered on the exams. Okay, Megan, over to you.
Okay, thanks, Jeff. Hi, everyone. I'm very excited to be talking to you today about electrocatalysis. Let me share my screen with you. And let's start. Okay, so as Jeff mentioned, I studied electrocatalysis in my PhD, and a lot of the concepts that you guys have been learning in terms of electron transfer and solution phase chemistry can be translated to electrochemical systems. And so I want to walk you through some of the ways in which that is the case, and also tell you a little bit about the research that I did during my PhD. So if you have any questions, interrupt me at any time. I'll try to monitor the hand raising function, and if Jeff and Maria and Alex could help me out, point out if there are questions, that'd be awesome. Okay, so a few goals that I have for you guys today are first, just understand how principles of solution phase electron transfer can translate to running electron transfer reactions electrochemically. Second, understand why when we do reactions that convert between chemical and electrical energy, why we absolutely need catalysis to solve this problem. And then lastly, see how the fundamental principles of electron transfer are translated to current research in electrochemical energy conversion. And in particular, I'll tell you a little bit about some of my research. Okay, so we would like to be able to move our power grids over to more wind and solar energy. Right now, we have the capability to use wind energy and to use solar energy, but we can only use these when the wind is blowing and when the sun is shining. And in order to move to a system where our grid is mostly dependent on these intermittent renewable energy sources, we then need a way to store the energy when we can use it. So maybe during the day, we can take solar panels, take energy from the sun, use the electricity generated from that to convert it into a stored energy source, and then use it later at night. So one of the ways that we can store energy is in chemical bonds of fuels. And what I mean by that is we can take small molecules and electricity is generated from solar or wind and convert that to a fuel. And in particular, what these types of reactions would look like are things like converting protons and electrons into hydrogen. And of course, the protons would come from some acid source, ideally water. We could be looking at taking oxygen and converting it to water. CO2 reduction to fuels is a really exciting area of research, and you could imagine a lot of different products that could come out of this. Here I've shown CO formate, methanol, ethanol, and methane. And what I want you to notice about all of these reactions, this is just a subset of the energy conversion reactions, is that all of them require proton and electron transfer steps. And today we're going to focus on electron transfer. So understanding the fundamentals of electron transfer and what governs when these reactions occur and the rates at which they occur is really important to designing efficient catalysts for doing any of these reactions. So in your last few lectures, you've covered how electron transfer occurs between molecules in solution. When we do electrochemical electron transfer, it usually occurs between an electrode and a molecule in solution. So this is inherently interfacial electrochemistry. It's occurring between an electrode and a molecule in solution, and there are going to be additional complexities associated with that interface. But reactions that you can, electron transfer reactions that you can do in solution, you could also do it in electrodes. So you guys looked at this example, I think before spring break, where electron transfer was occurring between ferrocyanide and this iridium hexachloride compound, and the iron compound was reducing the iridium. So what if we wanted to look at this reaction, but run it electrochemically instead? So whenever you're doing redox chemistry, whether that's between two solution phase species or at an electrode or photoredox chemistry, the important thing to look at first is the reduction potentials of the complexes to see where electron transfer is thermodynamically favored to occur. So I looked up the reduction potentials for these two complexes and found that the iron 2,3 reduction potential or 3,2 reduction potential is 0.36 volts versus the normal hydrogen electrode. This is 2 proton plus 2 electron goes to hydrogen, but we could use any standard reference. And 0.51 volts for the iridium complex. And one helpful way to visualize this is to draw out a number line with all the potentials. On the left, we have more reducing, so we'd go to negative potentials on the left, and then on the right, we have more oxidizing. And I can put this 0.36 volt iron 3,2 potential on this line, and I can put this 0.51 volt potential. And you can see that the iron 2 compound is more reducing than the iridium. We would expect that in net, this compound should be able to reduce the iridium complex, as shown in this top reaction. But an electrode, it's even simpler to think about on this number line, because we just know that if I wanted to replace this iron compound with an electrode, I just need to be at potentials negative of 0.51 volts, and then I should be able to reduce the iron compound. And what's nice about doing it at an electrode is if I'm looking at the reduction potential, I just need to know what it is. If I said, actually, I wasn't interested in the iridium compound, what I wanted to do was oxidize the iron compound, then fine, let's put the iron compound in solution. If I apply any potential greater than 0.36 volts, I should expect to oxidize it. What that looks like in a lab setting usually is you use a 3 electrode setup. So I took this cartoon from this Nature Review Chem paper from the Dempsey group. It's a clear model, but really you could use any type of beaker, very complicated electrochemical cells, any glassware that you can put 3 electrodes and a solution in, you can run electrochemistry in. So the most important electrode when we're probing electrochemical reactions is usually the working electrode, because this is where we're monitoring the potential of the reaction. So the chemistry that we're interested in is occurring at the working electrode. In practice, I would hook up all of these leads to something called a potentiostat, where I can either set the potential or the current. And now these are pretty straightforward to use in the sense that you would just type in the potential that you want versus a reference, and the potential that you're typing in is going to be the potential applied at the working electrode. You also need a counter electrode. Electrochemical reactions are half reactions, so we need to close the circuit with the second electrode. If I'm doing an oxidation reaction at the working electrode, I'll be doing a reduction electrode at a reduction reaction at the counter electrode, and vice versa. The third electrode is optional in terms of making the circuit work, but it's very valuable in terms of knowing the chemistry that you're doing. So anytime you see a potential value or a voltage, it is referenced to something else. And you can use a lot of different electrodes as your reference, but it has to be something that's stable and well known. There are some cases where it's challenging to get a truly stable, well-known reference in your medium, and in that case you can add a different redox couple to reference to, but it's still helpful to know roughly what you're putting in as your potential at the working electrode. So the value that you type into your potentiostat controller is going to be the potential difference between the working electrode and the reference electrode in practice. And then lastly, I want to note that the solution that you're using has to be electrolytic. So if you don't have any salt in your solution, you're just going to have extremely high solution resistance. It will be hard to pass charges through your solution. Any salt should be fine, but the properties of the electrolyte can affect things like electrocatalysis. So that's also an ongoing area of research. So as I mentioned before, we mostly care about the working electrode, and the chemistry that I'm going to show you and what we're going to zoom in on from here on out is going to be all chemistry that's occurring at the working electrode. Okay, so here we're zooming in on the working electrode. This rectangle here is representing the electrode. It's in a solution where we have electrolyte that's represented by these plus signs and minus signs, and then we have a molecule in solution that we want to do redox chemistry on. So you've discussed in this class outer sphere electron transfer versus inner sphere electron transfer in solution phase. And actually, outer sphere electron transfer, inner sphere electron transfer are two classes of reactions that can happen at electrochemical electron transfer as well. So first, I'll walk you through what's occurring in outer sphere electron transfer at an electrode. So in this diagram, you can see I've drawn these negative charges here at one side of our rectangle representing the electrode. So this is a negatively charged electrode. When I polarize negatively, I'm going to bring the positively charged ions in the electrolyte, these cations, up close to the electrode surface. And I can delineate this region of charge buildup next to the electrode surface. This is called the electrical double layer. And if you remember from electricity and magnetism, when I have two charged plates right next to each other, I have a capacitor. And so in the simplest way, we can think of the electrical double layer as a very tiny capacitor. And what's really cool about this capacitor is the distances across this double layer, depending on your electrolyte strength, can be on the order of a few nanometers. So it's really, really tiny. We can have really strong electric fields here to drive chemistry. What that looks like in terms of an energy diagram is if I, instead of plotting position on the y-axis, plot potential, this line here represents the electrostatic potential drop across this electrical double layer. So the potential difference is going to be the difference between the Fermi level, which I've denoted here, EF. The Fermi level you can think of as the energy of the electrons in the electrode and the driving force that they have to transfer or accept electrons from solution phase species. And here the solution potential is going to be the actual distance in the potential drop. You can't directly measure what this exact electrostatic potential difference is because you're measuring the potential difference between your reference electrode and the potential, but you can estimate it based on some factors that we won't get into today. Okay, so when I do outer sphere electron transfer between the electrode and a molecule in solution, I'm transferring an electron across this double layer. So it's starting at the electrode, it's transferring to the molecule in solution. The molecule and the electrode are not coming into contact, there's no bond formed, so we call this outer sphere. In inner sphere electron transfer, we start out from the same type of picture. Let's say that I want to transfer an electron to this proton in solution. I can denote the double layer. I can draw the potential drop across the electrical double layer. But now I'm going to form a bond directly at the electrode surface. So a bond's actually going to form between this proton and the electrode when I transfer an electron. And in this case, it's not the electron crossing the double layer, it's the ion crossing the double layer. So we can maintain the parallel of solution phase outer sphere versus inner sphere electron transfer and say, in this case, a bond is formed between the species that's accepting the electron and the species that's donating the electron, the electrode and the proton. But the additional thing to notice is that rather than the electron crossing the double layer, we now have the ion crossing the double layer. So that's a fundamental difference in what is occurring during the process. So what do I mean by charging an electrode and changing the energy of the Fermi level? It's a common misconception that when I charge an electrode and change the potential at the electrode versus the reference electrode, what I'm doing is filling and emptying energy levels associated with the band of the electrode. We are adding a couple electrons or a small number of electrons to the electrode itself. But when I change the potential at an electrode, most of the difference in potential that I'm gaining from that is coming from the electrostatic potential drop across the electric double layer. So on an energy diagram, what that looks like is moving the entire electrode up or down. So here we have our rectangle representing the electrode. We're denoting the Fermi level of the electrode at the potential of 0 charge, so no charge buildup. So when I want to put this on an energy diagram and polarize it negatively, in this case, I'm going to a more reducing potential, and I'm showing the entire electrode being raised in energy. All of the band states are moving together up versus this energy y-axis. And if I want to apply an oxidizing potential and polarize the electrode positively, similarly, I'm moving all of the energy levels in the band of the electrode down in energy together. So it's not a filling, unfilling, it's a shifting of all the energy levels. So keep that in mind. Oh, we have a question. Okay. Kelly.
Yes. So on the previous slide, with the outer sphere and inner sphere model, why is it a metal on the outer sphere case and a proton on the inner sphere case?
Yeah, okay. So here I'm just giving some examples. When we do outer sphere electron transfer, we usually look at molecules that have reversible redox chemistry. And in this case, I've drawn M to denote some molecular complex. It could be something like ferrocene or something like ferrocyanide that was used on the previous slide. You can transfer an electron to something else. You could even transfer one to protons if you had enough driving force, and we'll get that into a couple of slides. When we're doing inner sphere electron transfer, it's going to be with a species that the electrode can form a bond with. So something like ferrocyanide that's completely saturated is going to have a hard time forming a covalent bond with the surface. So that's why I chose protons as an example there. But it could be either thing in either case in theory. Just in practice, it's usually something like an ion for inner sphere and something like a coordination complex in outer sphere.
Got it. Thank you.
Are there any other questions right now? Okay. Oh, how do I call on people? I can't see your hands. Maria or Jeff, can you call on
So
people?
I think, yeah, Connor and Amy have questions as well.
Okay, great.
So
Go for
Connor,
it.
why don't you go ahead first?
Maybe you'll get to this, but is there a preferred mechanism for electron transport in these systems?
Yeah, so it depends what you're trying to do, and we will get to this in the context of catalysis in particular. They have pros and cons, and yeah, we'll come to that. That's a great question.
Okay, Amy?
I had a question about the potential difference in the two cases, that it looks like outer sphere has a much larger potential difference between the solution and the electrode than for inner sphere. Is this like a trend? So can you predict which mechanism it'll go by the potential difference? Or
In this case, these are, yeah, just two examples. You can't read into it more than that. So you can't predict this. The potential difference is actually going to depend more on the potential that you need to be at to run the reaction. So if we go back to the number line, the redox potential of the reaction you're trying to do and the electrode material that you're using. So the uncharged potential of the electrode is going to be dependent on the work function. So even to do the same outer sphere reaction, let's go back to ferrocyanide, this iron 2-3 couple that we were looking at earlier. If I were doing that reaction in solution and I used a carbon electrode versus a silver electrode versus a gold electrode, then actually the potential drop across the double layer would be different in all three of those cases because they all three have different work functions. And so in order to get to that potential, we would need to build up different amounts of electrostatic potential across the double layer. So yeah, you can predict the strength of the electrostatic potential drop based on knowing the work function of your electrode and the potential that you'll be applying, but not based on if it's outer sphere or inner sphere. Another thing to note that's related to that, but not quite what you're asking, is that in outer sphere, because you are not forming a bond between the complex and the electrode, in principle, it doesn't matter what electrode you use. You could use any conductive material, and you should expect the process to occur at the same potential. But at inner sphere, because we are going to care more directly about the properties of the electrode, which is both the work function of the material and the surface states on that material, the electrode identity matters a lot. So the reaction that I've shown is one that happens very easily on platinum. You can form platinum hydrogen bonds by transferring a proton and electron. But it's much harder to do that reaction on things like gold. And in fact, you would just generate hydrogen before you would observe the formation of a surface gold H bond. So outer sphere electrode doesn't really matter. Inner sphere electrode matters a lot. You guys have great questions. Thank you. Please feel free to continue to raise your hands. Okay, last class you guys talked about Marcus theory, and especially in the case of outer sphere electron transfer, Marcus theory actually works really well in describing the kinetics of electron transfer. Remember there was this solvent reorganization term in the Marcus equation, and at an electrode you can actually approximate it pretty well as zero, which is a little bit intuitive in that you have this solid that is not solvated in the sense that a molecule in solution is, but it's cool that it works out that nicely. Another thing to keep in mind is that Marcus theory is so very famous for this inverted region in which you increase the driving force for electron transfer and the rate actually slows down. This hasn't been observed at electrodes, and one hypothesis for why this is the case is that when I have an electrode, I increase the potential. At some point, I cap out on the rate. And if I go too high, let's say that this driving force is too high, and I would expect electron transfer from the Fermi level to the molecule in solution to be in the inverted region. Well, I have lots of other band states. I could just transfer an electron from some lower state as well. So basically, whatever the fastest possible electron transfer process that can occur is the one that's believed to occur. And the experimental evidence for this is that you see this Marcus type behavior until you get to the maximum rate of electron transfer, and then you just see it plateau. The rate doesn't change anymore with increasing driving force. Any questions about this? Okay, I will move on to our next section, which is why do we need catalysis to convert between chemical and electrical energy? So let's say that I'm running an electrochemical energy conversion device, and at the cathode, I'm going to do the hydrogen evolution reaction where we have 2 protons and 2 electrons make hydrogen. And at the anode, I'm splitting water into oxygen, protons, and electrons. Let's again look at the hydrogen evolution reaction in particular. So this, before we do that, the energy difference between the thermodynamic potential for doing hydrogen evolution and the thermodynamic potential for taking water and splitting it to oxygen, protons, and electrons is going to be the minimum energy I have to give that system in order for it to run. This is just thermodynamics. So in this case, that's 1.23 volts. But that's assuming that there's no activation energy to either of these processes, which is, of course, unreasonable. And so this additional energy that we're actually going to have to apply to run the reactions is called the overpotential. It's symbolized by eta, and it's literally just the difference between the potential that you're applying and the thermodynamic potential for the reaction. So if I want to do hydrogen evolution and I'm at minus 0.5 volts instead of at 0, then I have 0.5 volts of overpotential. So let's say I don't catalyze this reaction at all. I just want it to run. It's supposed to run at 0 volts versus RHE. I'm now asking 2 protons and 2 electrons to all come together at the same time and make hydrogen molecules. This is going to have a ridiculously high activation barrier and basically be kinetically impossible. It's a quaternary reaction. So this reaction probably isn't going to just occur at the thermodynamic potential. In this case, whatever potential is way up here is going to be my overpotential for the reaction. Let's say, okay, we're not ridiculous. We don't want this quaternary reaction to happen. We just want a proton and electron to come together to make it H atoms, and then two of these H atoms can combine. So the outer sphere potential, and this gets back to Kelly's question a little bit about which reactions are possible, inner sphere or outer sphere. If I were to do the 1 proton, 1 electron outer sphere reaction where the whole thing occurs in solution, I would need to go to minus 2.2 volts. So the entire cell should be running close to 1.23 volts. 2.2 volts of overpotential for 1/2 reaction is going to be completely untenable. So we're going to rule that out as a possibility. Instead, if we use a catalyst, so let's say we have I'm just representing the catalyst as M, and this could be a surface site, but it could also be an M for a solution phase species. Oh, actually, this one can't be a surface site because the way I drew it. This is an M for a solution phase species. You could imagine generating intermediates that can stabilize hydride species or H atom species and then go on to make hydrogen. So in this case, I've shown maybe you have one step where you reduce your metal species by 2 electrons and make an M2 minus, and then you can form a hydride, and then you can protonate that and make hydrogen. And the barrier to each of these steps is something that we can access, and so catalysis makes this reaction possible. And you can imagine that it just gets more complicated if we go to more complicated reactions. So let's say instead of hydrogen evolution, I want to take CO2 to methanol. I still have my minimum energy requirement. I still am going to have to apply some overpotential. But now, if I don't catalyze the reaction, I'm asking 7 species to come together simultaneously. The activation barrier is going to be way too high. The overpotential is way too high. It's never going to happen. And so we're going to need catalysis. And now we can start thinking about what would a good catalyst look like. And in the broadest of strokes, a bad catalyst is going to have a lot of steps with a lot of high energy intermediates. And a sort of dogma in the field is that if you generate a lot of really charged species, that's going to end up with high energy intermediates because charged species just tend to be higher energy to form. But if we could minimize the number of steps and we can keep the activation barriers low for all of them and keep the energies of the intermediates as low as possible, then we have more efficient catalysis. So we're aiming for the green line, not the blue line, but the blue line is possible, the red line is impossible. So then when we think about catalysis research, we want to be able to understand the factors that are going to govern each of the proton and electron transfers, because taking a step back, remember, we're starting with a small molecule. The reason we have so many reactants, so to speak, is we're doing lots of proton transfer and lots of electron transfer steps. And so those are the steps that we need to zero in on and understand the energies of intermediates that would be associated with transferring an electron or transferring a proton, and also what governs the rate of electron and proton transfer in these systems. So we've talked about outer sphere versus inner sphere, and another way to bin this is maybe molecular and heterogeneous. Molecular catalysts, this gets to the question of, is one better than the other, outer sphere or inner sphere? So molecular catalysts are great because we can use all of the principles that you've been learning in this class about inorganic complexes to design a molecular electrocatalyst. We have these discrete electronic states in the molecular orbitals of these complexes, and we can use principles of inorganic chemistry to rationally design a catalyst and say, okay, this one should be more efficient, this one should be less efficient. And these are all going to be based around concepts that you've discussed in this class. So I can think about what oxidation state would be good for stabilizing an intermediate. I can think about the geometry of my ligand design. Do I want my compound to be tetrahedral or octahedral, or do I want a unique geometry that I can design from ligand design? Do I want to tune the energy levels of the molecular orbitals by incorporating electron donating and withdrawing groups? And this is actually a really common strategy when people find a molecule that's a good catalyst. They can tune the reduction potential of that compound and therefore the overpotential that you have to apply by incorporating electron donating or withdrawing groups just to move the energy levels of the valence orbitals. And you can, any other molecular design principle, you could incorporate sterics to control kinetics of Maybe you want it to be a bimolecular reaction. Maybe you want to prevent bimolecular reactions between two metal complexes. So we have the entire suite of molecular design principles available to us when we use a molecular solution phase catalyst. Now, with heterogeneous catalysis, if I'm doing the reaction at the electrode surface, all of this goes out the window because we're not dealing with molecular orbitals anymore. We instead, in a metal, have so many energy levels so close together that it's better to think of it as a continuum of electronic states. So here I'm representing gold, but any metal, we're going to have this band structure. That doesn't mean we don't have ways to tune the catalyst. We can change the electronics of the band structure and the sites at which you can bind species at the electrode itself. So some ways to change the surface chemistry would be to essentially incorporate defects into it. No surface is perfect. Even if I just take a piece of platinum, there are going to be different facets on it. There are going to be different defect points on it. Facets and grain boundaries are specific types of defects, essentially, and we expect some sites to have better catalytic activity than others, so it's not that we have no design principles. We can also change the band structure of the electrode using alloys, basically tune the overall electronics of it. But it does mean that we don't have as easy access to knowing which sites on the surface are doing the chemistry. And we don't have as easy of a way to probe that or to alter it on a molecular level. So that's one challenge. I already walked you through the different mechanisms. So molecules are going to be going through outer sphere. Electrode surfaces are going to be going through inner sphere ET mechanisms, and that does have a benefit in catalysis. So let's take hydrogen evolution reaction as an example. If I have a molecule that's going to catalyze the reaction, it's acting as what we would call a redox mediator. So the molecule that's doing the catalysis, which I've shown here as M, is the substance that's going to be accepting electrons from the electrode directly. So let's say first we transfer an electron to M, generate M minus. The reason it's called a redox mediator is that the driving force then for binding the proton and forming this MH intermediate is coming from the reduction potential of the molecule, not from the electrode. So I can change the potential of the electrode to reduce more of the molecule, but increasing after a certain point, after I've reduced all of the molecular catalyst that's next to the electrode, increasing the potential at the electrode further isn't going to have a direct impact on the driving force for forming this MH species. That's just coming from the intrinsic thermodynamic properties of the molecule. So that can be a downside. Then it could go through subsequent steps to complete the catalytic cycle. And maybe this is a little clearer in contrast. If I'm doing catalysis at an electrode surface, I'm going to transfer the proton and the electron in the same step. This has to do with charge balancing. I can't just transfer an extra electron to an electrode and hold the potential constant. I have to balance the charge there to hold the potential constant. And similarly, if I bring a proton to the surface, I can't form a bond without inducing electron transfer. And because it's happening directly at the electrode surface, I can just continuously increase the potential at the electrode to increase the driving force for this electron transfer step. It's not going to be pinned by a reduction potential of a molecule. So that was a lot of mechanistic steps. I will stop here for a moment if anyone has questions. Okay, let's keep going. So now I want to tell you a little bit about my research, which was looking at bringing molecular level precision to heterogeneous electrode catalysis. So I've already set up the problem a little bit. We like molecular catalysts because we have so much control over them, and we can get structure function relationships, and we can understand that Marcus theory is governing the rate of electron transfer in the outer sphere steps. But at a surface, we have so little control over individual sites or knowledge of what the active sites are that it's hard to have as a molecularly precise view of what's happening on the surface, which makes it really hard to rationally design catalysts. So if I can give you a visual for that, we have our molecule on one side, we're doing stepwise electron transfer, substrate activation, outer sphere process, lots of molecular control. If I'm instead at, this is back to our gold electrode, but any electrode, I get the benefit of continuously increasing the driving force by increasing the potential at the electrode. I have this inner sphere pathway. These could be really efficient in catalysis, but I don't know what the active sites look like. And to complicate things even further than just having it harder to characterize a site on an electrode surface, usually it's thought that only a very small number of sites on the surface are participating in the catalytic reaction, or at least contributing to the majority of the rate of catalysis. Whenever I measure a rate, I'm measuring an aggregate rate. So if I have more than one site participating on a surface, then I can't deconvolute that. I'm only getting one value for the entire rate. Usually when I polarize electrodes, in electrolytes, so under catalytic conditions, the surface can be rearranging and changing, it's dynamic, it's moving. If I do spectroscopic studies during the reaction and there's more than one site participating, or sites that aren't participating, I don't know if I'm looking at an intermediate or if I'm looking at just some poison species that's sitting there watching the reaction occur. And so in order to tease out what's happening at heterogeneous electrode surfaces, we really need to design a system where we have molecular level control over a metallic active site. So one approach at first, you might think, okay, great, let's just take a molecule and let's attach it to an electrode surface. So here I've shown this through a thiol bond, and there are actually a lot of studies where people have essentially tethered or molecularly tied molecules to surfaces. And this has given us a lot of the information about how we know that Marcus theory governs outer sphere electron transfer at surfaces. It's also useful in the sense that the catalyst is immobilized on the surface, but it doesn't solve the fundamental problem of telling us about metallic active sites, because there's still a barrier to electron transfer between the electrode and the catalyst active site. So in this case, I've drawn this aliphatic linker, and the majority of these are insulating linkages. And so the electron still has to cross the double layer to get to the metal site. We see the exact same form of electron transfer that we do for molecules in solution. So in my research, we thought, what if we could replace this insulating aliphatic linkage with a conductive aromatic linkage? Then maybe we could electronically couple a molecular catalyst to an electrode such that it behaves like a metal surface site instead of like a molecule that's just been attached to the surface. So we believe that we've developed this system. We call it graphite conjugated catalysts. And I'm going to walk you through the data that leads us to believe this is the case. So before I start going through data, I want to note that because we're at the interface of molecular inorganic chemistry and materials chemistry, there are going to be a lot of techniques that you may or may not have seen before. So if you see plots that you've never seen and you're not sure how to interpret the data, I'll do my best to give you the takeaway and why we made the conclusion that we made. But yeah, don't be intimidated by that. So graphite conjugated catalysts. I'm giving you a sense of what electrode we use from the first word. Graphitic carbon is actually conductive. This is just pencil lead and similar variants. We typically use something called glassy carbon, but we use tons of different graphitic carbons. They're made up of these layers of graphite sheets, which I'm showing here. And there are two components of these layers. There's the basal planes, which are the graphene-like flat parts of the sheets. And then there are the edges. And if we zoom in on the edges of each of these graphite sheets, we see a lot of oxygenic functional groups that are familiar to us from organic chemistry. So we have alcohols, we have carboxylic acids, orthoquinones, ketones, lactones. So we saw this as an opportunity of, hey, we know what to do with these types of groups from organic chemistry. Why don't we just treat the graphite electrode like a giant molecule and do chemistry at these sites? So we found that when we take these graphitic carbons and we soak them in solutions with diamines overnight, we can form these aromatic pyrazine type linkages. So pyrazine nitrogen is here. And we then wanted to characterize it when you're doing molecular synthesis, you have NMR, you can get a crystal structure, you can easily take UV vis and IR, and all of these things become more challenging or completely non-informative when we move to our carbon. We just took our carbon, we soaked it in ethanol with this diamine, and now at the end we still have a black solid, and it's insoluble. So we're gonna have to use different characterization methods. So if we look at X-ray photoelectron spectroscopy, or XPS, here we're looking at the nitrogen, and XPS takes advantage of the photoelectric effect. So we're looking at ionization energies and correlating what we observe to what we know about different elements in different environments. So the binding energy that we found for the nitrogen 1s correlates with reported values for pyrrhocinic nitrogen, indicating that we only have one type of nitrogen on the surface, and then it's pyrrhocinic. We could also scale up the reaction by using carbon powders instead of carbon electrodes. And then we can look at X-ray absorption spectroscopy. So you can think of X-ray absorption spectroscopy as a photons in, photons out experiment, follows Beer's law. Imagine UV vis, but you're using X-rays instead of UV light or visible light. And here what we're looking at is core transitions. So 1s to 2p of the nitrogen. And you can see we observed this transition. What was most helpful in characterizing this compound was, in red, we synthesized this model compound, and we also got X-ray absorption spectroscopy data for the model compound. And when we overlay them, you can see they overlay really well. So this indicated to us that we are in fact forming this pyrrhocinic species on the surface, and that's the only species we're forming in a reasonable amount. So in this sense, we can already start to think of our having this molecular level knowledge of a site on the surface. So I was interested in the mechanism of electron transfer at these sites. So for each of the graphite conjugated catalyst, or GCC sites that I'm going to walk you through, I'm going to also show you data from molecular analog. And in this case, I was looking at the water-soluble pyrazine shown here. And now we're going to start seeing a lot of electrochemical data. So what I'm showing you here is a cyclic voltammogram. On the x-axis, we have potential. So if we go more to the left, we're going to more negative potentials, more reducing potentials. Down current is cathodic, so here's reduction, and then coming positive. Here we're looking at oxidation. Y-axis is current. I point this out because there are different conventions. So here I'm showing the IUPAC convention. In the US, it's pretty common for people to also use what's called Texas convention. So if you see that, just take the plot and do a C2 rotation, and you'll go back to IUPAC convention. So you can see here, we have this reversible redox feature. The compound is getting reduced and then comes back, reversibly oxidized. This process is associated with the 2-electron, 2-proton reduction from the pyrazine to dihydropyrazine. And if we have this species on the surface, we might expect to see something similar when I don't add anything to solution and I just put the functionalized electrode in the same electrolyte. And we do. You can see that the potential has shifted a little bit positive, and that the peak has broadened out. But qualitatively, we still see this reversible process at a similar potential. And so we started by assigning this process to this 2-proton, 2-electron reduction of the phenacene to a dihydrophenacene type species on our electrode surface. We then moved to a non-aqueous electrolyte. So this is an acetonitrile. And in this case, the model complex was phenacene, just dissolved in solution. Phenacene shows this reversible 1-electron reduction. So here's the compound getting reduced by 1 electron, reoxidized, beautiful reversible wave. And now, based on what we saw in water, we would expect to see something analogous with just the electrode and nothing in solution. But instead, actually, we saw nothing. So that was interesting. In water, we're observing this analogous electrochemistry, but in acetonitrile, all of the redox chemistry seems to disappear at that conjugated site. So we thought, what's the difference between these two systems? In the aqueous case, we had protons around. The reaction was different. It was a 2-proton, 2-electron reaction. And in acetonitrile, we didn't. It was just an outer sphere electron transfer. So we thought, okay, maybe what's happening is when we have protons around, we're forming nitrogen and hydrogen bonds and doing inner sphere chemistry, so to speak. But since we were already at a graphitic electrode, when I just added these 2 additional aromatic rings to the electrode, maybe I'm just extending the electrode a little bit, and I shouldn't think of that as something that I can transfer an electron to. And so to test this hypothesis, we added an acid source into acetonitrile, and you can see that we do start getting this broad wave back at a potential where we would, closer to where we would expect proton-coupled electron transfer to occur. So from here we get, when there are protons around, we see redox chemistry at these pyrocynic GCC sites, but when there aren't, we see nothing. So in this sense also, we started to build up a molecular picture. In this case, we have testosteronic acid. You can imagine forming the bond with the nitrogen while we transfer the electron to that bond inner sphere. What's nice about this system is if you can synthesize the diamine, you can put it on an electrode. So we wanted to look at some classic complexes that have been studied in other systems for outer sphere electron transfer. We chose, this is a Rubippi analog, so it's got methyl groups on it to shift the potential a little bit. But this is just a classic, really fast outer sphere electron transfer molecule. So we thought it would be an interesting case to probe the mechanism of electron transfer at GCCs. We can characterize this. I'm showing you some of the characterization. This is the XPS. From here, we can see we have the ruthenium on the surface. We have, unfortunately, in XPS, the main peak for ruthenium overlaps with carbon perfectly. So we're using these tiny little Ru3P peaks, but we can integrate them and we can get a ratio of 1 to 7. We're expecting 1 to 8, so that's pretty close considering our tiny peaks we're working with. We can also zoom in and do high resolution XPS on the nitrogen, and we see that we have a peak associated with metal-bound pyridinic nitrogen and a separate peak associated with the pyrocynic nitrogen in the 3-to-1 ratio that we expect. So now let's look at the electrochemistry of this system. At the bottom here right now, what I'm showing you is the beautiful reversible ruthenium 2,3 wave. So classic cyclical thermogram duct shape. At 0.9 volts. But then when I take CVs of the conjugated system, I don't get any redox features. So this was a little bit more surprising than just not seeing redox features for phenazine attached to an electrode. We didn't simply extend the electrode by 2 aromatic rings. We added this entire ruthenium molecule here, and we're seeing nothing. So that was interesting. Since we had the proton-coupled electron transfer reaction to study at just the phenazine that was conjugated to the electrode, we wanted an inner sphere probe for a metallic complex. So we chose this rhodium molecule. It's a rhodium CP star phenanthroline chloride molecule, and it does reversible 2-electron chemistry. So here I'm showing you the CV. We're going from rhodium 3 to rhodium 1, and when it gets reduced, it loses this inner sphere chloride. Then when you oxidize it, it comes back, picks up the chloride again. Okay, when we conjugated this rhodium complex onto the carbon electrode, we actually do see a redox wave. So that was interesting. Rubippi compound, no wave, rhodium compound, we see a wave. But now, since we were completely erasing the redox chemistry in outer sphere systems before, there was no reason for us to assume that the process we're observing here at the conjugated rhodium molecule is exactly the same as the redox process that is undergone by this rhodium molecule in solution. So we looked at the stoichiometry of this reaction. We correlated the rhodium on the surface of the electrode to the charge in the wave. And the first thing we noted is that this redox process for the graphite conjugated system appears to be a 1-electron process, not a 2-electron process. So that was the first key difference. Then we were interested in, is this an chloride coupled process? And so one way to probe that was to swap out the chloride ion for a different ion. So you can see that when we substitute bromide in the electrolyte for chloride, we see the wave shift. So that was an indication that it was coupled to the chloride or to the bromide. We also can look at the concentration dependence on the position of the wave. So if you remember the Nernst equation from previous chemistry classes, we would expect different shifts in the potential if it's a 2-electron 1-chloride process or if it's a 1-electron 1-chloride process. And we see roughly 60 millivolt shift in the potential per order of magnitude change in chloride concentration, which was consistent with a 1-electron 1-chloride process rather than a 2-electron 1-chloride process. So we're going to fill in the reactants here as rhodium compound minus the 1 chloride plus 1 electron. And our next question was, okay, if we're doing completely different redox reaction where we have a different number of electrons, what's going on at the rhodium? And the molecule, we actually expect this to be a 2-electron process because the rhodium-2 complex would be so high energy that it would already have enough energy to go all the way to the rhodium-1. But in this case, we're doing a 1-electron redox reaction. So what's happening at the rhodium site? Is it actually a rhodium-2? And we can probe this by looking at X-ray absorption spectroscopy again. So this time we're going to look at X-ray absorption spectroscopy at the rhodium. And the cool thing about this experiment is we did it in situ. So these experiments can't be done in-house. You need to go to a synchrotron, and we went to the Argonne National Lab. Here you can see our cell setup. You can see we did it in situ, and you can see my cell looks a little different than the one I drew out in the cartoon. The electrode facing us is the reference electrode clipped there, the counter electrode over in this other compartment. And then the working electrode you can't see, it's facing away from us. The detector is coming in, hitting it, and then coming back, or this is the beam over here, coming in, hitting the electrode, and then going to the detector in fluorescence mode. It's easier to see in this cartoon. So at the working electrode, we are using the electrode as a window. At the energies that we're at, which are above 23,000 electron volts, the carbon is just going to be X-ray transparent. So we just functionalize one side of the carbon electrode, the side facing solution. We have the X-ray coming through the back, and then we're detecting. So this is the X-ray absorption spectrum, or a zoomed in part of what's called the K-edge for the GCC rhodium when we have not applied a potential. So we're looking at this 1s to 5p transition. We expect that we will observe this line shift 1 to 3 eV if we see the oxidation state change. And maybe you're looking at the x-axis and you're thinking, we're at 23.23 keV, how are we going to notice a 1 to 3 electron shift? You actually can, and we can see that in the model complex. The spectrum changes pretty dramatically when it shifts between the rhodium-3 and the rhodium-1. Okay, but in this case, we polarize 120 millivolts negative of our observed wave, and we don't see any change in the spectrum. It's staying exactly the same. And we go 240 millivolts past the wave, and we still see nothing. So we've completed this redox process. The XAS spectrum didn't change. This indicates to us that the oxidation state of the rhodium is not changing during this redox process. So if the electron isn't going to the rhodium, where is it going? I don't know if you guys have talked about non-innocent ligands, but if the electron's not going to the metal site, it's got to be going to the ligand. And what's cool in our case is that our ligand is the carbon electrode. We basically have the world's largest non-innocent ligand here. So the electron doesn't have to be centered at the rhodium site. It can be centered in any of the band states of the carbon to counteract this chloride charge. I'll stop here for questions. Okay. So what's going on here? We have this pyrazine system where when we had protons around, we see a wave. We don't have protons around, we don't see a wave. We have this Rupippi complex, we don't see a wave. We have this chloride process that's totally different than the process for the molecule, and we do see a wave. So we constructed a model that would explain all of the results that we were observing in terms of outer versus inner sphere electron transfer. So for the molecule, or you could imagine a molecule that's tethered through an insulating linkage, let's go back to these diagrams we had earlier where we're applying potentials and moving the energy of electrons in electrodes up and down. So here, on the left here, I'm showing the electrode in the Fermi level. So this gray are filled band states, this tan are unfilled band states. The ruthenium molecule is out here in solution, and I've denoted the ruthenium 3,2 potential. So if I want to oxidize the ruthenium in solution, I need to apply an oxidizing potential. We're going to move all of the orbitals, energy of the orbitals in the electrode down. And when they drop below the Ru3,2 couple, there will be enough driving force to transfer an electron from the ruthenium in solution to the Fermi level of the electrode, and we'll see current flow. But what about on the GCC? In this case, if the ruthenium is electronically coupled to the electrode, now when I apply the potential, I'm applying oxidizing potential, I'm getting below technically the Ru3,2 potential in solution, but if the ruthenium is electronically coupled to the electrode, then when I move the energy of the band states up and down by applying a potential, I'm going to be moving the energy of the molecular orbitals in ruthenium up and down at the same time. And so even though I am changing the potential and changing the driving force for electron transfer between the electrode and the solution, I'm not significantly changing the driving force between the electrode and the ruthenium species. These are just moving together. But then we have this question, well, then why would you ever see electron transfer at a GCC site? And so let's go to the rhodium case and see what's happening there. For the rhodium molecule in solution, it's the same thing. We're doing a reduction instead of an oxidation. So this time I'm going to have my electrode Fermi level here, and I'm going to apply a negative potential, and so move all of the energy levels up relative to the rhodium 3 complex in solution. When I have enough driving force, I'll transfer electrons from the Fermi level of the electrode to the rhodium species in solution and simultaneously lose this chloride ion. For the graphite conjugated version, this time I'm going to apply a potential, same thing. The orbitals of the rhodium are going to move along with the orbitals in the band states of the carbon electrode, and so I don't increase the driving force for reduction of the rhodium species when it's conjugated, and this is why I don't see the oxidation state of the rhodium change. But this case is different because now I have this labile chloride here. And the chloride ion is negatively charged. It can form in break bonds with this rhodium site. And so when I generate this negative charge right at the surface of the electrode, I'm building up an electric field. And eventually, this negative charge buildup at the electrode is going to drive the negatively charged chloride away from the surface. So I can denote the potentials that we're used to thinking about, the Fermi level of the electrode, the rhodium 3,1 potential for the molecule in solution, but now there's another redox potential that we can consider, which is the potential required to drive chloride ion to bind to the electrode at the rhodium site or to leave the electrode at the rhodium site. And what's exciting about this model is this is exactly how we think of electron transfer at metal sites. So earlier when I talked about forming platinum hydrogen bonds at a platinum surface, this is a process in which you bring a proton to the surface and you compensate for that charge with 1 electron. And normally you would think in solution of a hydride is a 2 electron, 1 proton process. Why is it a 1 electron, 1 proton? we care most about balancing charge when it comes to holding potential constant during an experiment. So in the metal surface in platinum, we see that as a 1 proton, 1 electron reaction. For forming and breaking bonds with chloride at GCCs, we're seeing this as a 1 chloride, 1 electron reaction. So this is cool. This is exactly the mechanism that you would observe if it were behaving as a metal. So it seems that we do have molecular fidelity at a metallic surface site. And I will pause here for questions again. That was a lot of information, very fast. Okay, so let me take you back to this first slide that I showed you at the beginning of this story, and note that in fact, it seems that electron transfer and substrate binding, in this case chloride, are coupled, and that our graphite conjugated sites are behaving like metal surface sites. And we use this platform after that to probe the thermochemistry of proton coupled electron transfer at surfaces, so come up with a model for when do we observe proton coupled electron transfer at a surface site if I can't trust the redox potential of the molecule. If it's going to be a different process than my molecular analog, then what should I be pinning it to? And then we also have been looking at this in the context of catalysis. And what's nice about electrocatalysis in general is anytime you're collecting data at an electrode using a potentiostat, you're collecting kinetic data. So you can get a lot of information about the rates of electron transfer and rates of catalysis pretty rapidly. And so I'm going to jump to the end rather than walk you through all of this kinetic data. But I want to give you a sense of what happens if we look at an actual catalytic reaction instead of just forming and breaking bonds with chloride at a surface. So let's go back to this slide I showed you earlier. In a molecule, we typically see mediated pathways. So these would be stepwise. The kinetic markers that we would be looking for in this type of pathway are how many electrons were transferred before the rate limiting step, what's the reaction order in proton donor, what is the potential dependence on the rate. So you can actually write out, based on Marcus theory, these potential dependencies that you would expect to see for each of the different possible mechanisms of electron transfer. For example, in this case where we're transferring an electron, and then if we had rate limiting proton transfer, we would see 60 millivolt. For every 60 millivolt change, we would see an order of magnitude change in current. But if instead this first electron transfer rate limiting, we would see 120 millivolts were needed for a 1 order of magnitude change in current. When we look at a heterogeneous inner sphere pathway, we would expect that proton transfer and electron transfer have to be concerted, which means we would see rate limiting electron transfer, either the first or second step, and we would also see rate limiting proton transfer. And we can again look at how many electrons were transferred before or at the rate limiting step, and we can look at the reaction order in protons. So we did this for GCCs. It turns out that this rhodium molecule that I've been introducing you to actually is a known hydrogen evolution catalyst. So it's been studied reasonably extensively in both aqueous and non-aqueous electrolytes. And the kinetic data that others and that we reproduced have observed show that the pathway is consistent with fast pre-equilibrium electron transfer followed by a rate limiting chemical step. Depending on the exact conditions that people use, it could be the first proton transfer or the second proton transfer, and it could be this first couple or the second redox couple. But in all cases, we're observing data that are consistent with stepwise pathways, which is what we would expect from a redox mediator as a catalyst. When we looked at the graphite conjugated rhodium species, we found that the kinetic data were consistent with rate limiting proton transfer and rate limiting electron transfer. So concerted proton electron transfer. We saw this in the potential dependence was consistent with the first electron transfer step being rate limiting. We found an HD kinetic isotope effect that was consistent with rate limiting proton transfer. we found a pH dependence that was consistent with this mechanism as well. And so it seems that by conjugating it to the electrode, we're moving it from an outer sphere pathway to an inner sphere pathway. And the practical implication here that was cool to observe is that we could have the molecule act as a catalyst even in pH conditions, when it was conjugated, in pH conditions in which there would be no catalysis at all in the molecule. And that comes directly as a consequence of a mechanism that's occurring in inner sphere, where when I continue to increase the potential at the electrode, I'm increasing the driving force for catalysis in an inner sphere system, versus I'm really stuck with the redox potential of the molecule if I'm using a redox mediator. Okay, so thanks for letting me share my research story with you. I hope that you got a sense of how graphite conjugated catalysts can be used to bring some molecular level insight into heterogeneous electrocatalysis. Now that we have these types of active sites, you can imagine looking at spectroscopic studies where we actually know what the active site looks like. When we're getting kinetic measurements, we know that we're looking at the conjugated sites and that they're all similar, so that we can actually get structure-function relationships from them. And since they in fact do catalysis, we can start looking at the factors that control catalysis and which of our design principles from molecular solution phase electrocatalysis translate to heterogeneous catalysis and which ones don't. So this is a direction that I'm very excited about. And now just to revisit what we've covered, I hope that you can see that electron transfer and the principles that you're learning in this class have a really important role to play in electrochemical electron transfer, and particularly in energy conversion, where we're converting between chemical and electrical energy, even at the very fundamental level, and then long-term into designing more efficient catalysts. And I'm happy to take questions.
Okay, thanks very much, Megan. We've got some time for questions. If anybody has any questions, yeah, Kelly, go ahead.
Yeah, so on slide 19, I think you can see that the graphite has multiple like oxygen groups on it, and I'm assuming this pyrazinic attachment only is able to attach to a specific type of group. So how do you manage all the other groups that are not able to be replaced by the diamine?
Yeah, so you're right that we're only going to be able to form this pyrazinic linkage at orthoquinone sites, and also that one potential challenge would be, what if we form mono amine linkages if there's not an orthoquinone site? So we do an acid treatment to cleave all sites that are not these pyrazines. The rest of the oxygen groups are still there. They're native to the carbon. They're still there when we do this chemistry, but they don't have any signals that would show up in our CVs or other measurements. Actually, one of the challenges with this method in general is that we can only functionalize at some sites on the edges, as you're pointing out, and so our overall coverage is pretty low, which does make spectroscopic studies more challenging, although you can see even the in situ study we were able to get data, so that was exciting. Yeah, but the entire basal planes, we should just assume there's nothing. Does that answer your question?
Yes, thank you very much.
Okay, other questions? All right, looks like not. So thanks very much, Megan. And I want to remind everybody, we'll have another expert lecture on Tuesday. That will be from Dr. Brandon Barnett on organometallic catalysis. So everybody have a great weekend, and we'll reconvene.
I'm sorry.
Oh, David, did you have a question?
I'm sorry. Yes, I didn't know how to do the raise hand function.
Oh, go ahead, David.
Thank you. I wanted to. So this is a question for both of you, Professor Long and Professor Jackson. So I'm curious as to what the intersection is between your two fields are. So MOFs and this type of catalysis. So I mean, one can envision instead of the molecular active site being tethered to graphites, it's being tethered to a POF or a MOF. You could maybe form a porous electrode with more surface area. So I was wondering if Dr. Long, you could please respond.
Yeah, actually, I think, and it is something a lot of people are doing research on. And I know Megan has thought about this as well. It's not something that's really been, I'd say, extensively studied yet, but it is an active area of research. And in terms of conductivity, getting the sort of conductivity that you see in graphite in those electrodes that are used in, say, glassy carbon or other electrodes, it's hard to achieve that sort of conductivity in a porous framework like a metal organic framework, which we'll discuss later in the class, or a covalent organic framework. So there are not a lot of examples where you could have a similar sort of effect, but there are some that are getting close. And so actually improving conductivities in these frameworks is an important step towards that. Megan, do you have anything you want to add?
Yeah, I think that it would be really good to increase active site density and to increase surface area. And as Jeff said, you're asking a lot of your MOF to have it be conductive and stable under polarization, stable in your electrolyte conditions. So these are all things that would need to be worked out, but it would be cool to be able to solve these problems, yeah.
Okay, looks like we have another question from Amy.
Yes, this maybe is kind of along that vein of like finding active sites. In that, were there any like SCM or AFM studies to like examine like the number of step edges or edges? Because I think like the special groups are only occurring at those edges, or was there like could you fracture or stress the graphite to make like more step edges?
Yeah, so different types of graphitic carbons inherently have different numbers of edges and of oxygenic groups. So what we did to increase the number of them was we would oxidize the electrode electrochemically. We would take it to like 3 volts and oxidize the heck out of it. And then we would find that we could increase the loading by an order of magnitude. But yeah, we personally visualize this using STEM, and you could see it light up a little bit, but there have been a lot of studies done in the past extensively on different types of carbons and the functional groups available to them. Depending on the pretreatment, you might get more orthoquinones or you might get more carboxylic acids. So yeah, that's a fantastic question. Ways to increase the sites on the carbon. Definitely increase the sites of graphite conjugated catalysts.
Thank you.
Okay, other questions? All right. If not, then I'll see everybody on Tuesday. Have a good weekend.
Okay, thank you all.